Swayam Prabha, free DTH channel for education.
Okay, so what I will do in this class is, what I'm going to do now is I'll quickly go through maybe an intuitive explanation as well as mentioning the results from the last couple of videos that I have shared with you. And then we will go through something for which some of you are waiting eagerly, and I was keeping you in the waiting mode. That's about how is it in the first place related to anything with Fourier transform. So that's what the signal interpretation of it is, what we are going to see in this class. Okay, that's what we start to look at that aspect in this class. Okay, so let me share my screen now. Along with that, let me also mute my video. Sorry, stop my video. Okay, I'll go to the stop me anywhere if something is not clear. But if you have not gone through the derivation, where you have any questions, that you could perhaps first go through that and then come back for any clarifications there. Okay, so let's first hope you are also with your notebook so that you could work along with me. First, let us write the differential equations that we have got for the block equation. So hope you all remember that. That's equivalent to dm bar by dt equal to, you could tell along with me, maybe you could give me the lead here. If you remember, you should be remembering at the end of this course, this is a cross product of the m bar with gamma times b bar plus another term. That's the next two terms will be, I could write it as minus there. So this is the one term. Okay, and then if you look at the free induction decay term or transverse relaxation term, that is minus 1 by t2, and that's in the xy plane. So you could equally write it as mx times x cap plus my times y cap. And then there is a term due to longitudinal relaxation, right? This has to do with only z cap, and mz minus m naught, the initial value, or the m naught value, final value, times z cap, right? So this we already discussed earlier. This is something that causes torque and eventually the precision that you observe is dictated by this term, and this term is the free induction decay, you call it, or this is also due to the transverse relaxation. And this is the term which is related to the longitudinal relaxation, right? This is what we have done in the last Zoom class also. And then we have this BC, all the B bar field here will be always directed towards Z cap. This is just, you gave an excitation in the XY plane using B1 coil and you are done with it. Now whatever field you are applying would be in the Z direction only. So the case you would be considering here is always, if you can call this as X, Y, Z, your B bar is essentially in the Z direction here, right? And maybe the initial cases that we consider would be the case where you have a constant value throughout for all values of X, Y, Z. At every point, this B bar equal to B naught into Z cap. And then this is your transverse plane, right? XY plane is referred to as the transverse plane. And this is, of course, your longitudinal axis is this one. So you will be looking at values in both the directions, but more particularly later, we will be more focusing on the transverse plane, right? This you refer to this value as mxy, and even sometimes you would be simply referring it to as m itself as we move on. That's the case in most of the textbooks, because that's where you will be receiving the signal and analyzing, so that usually referred to as m itself. Okay, then we made some initial analysis, okay, both in the video lecture and the earlier class also. Suppose there is no T2 decay, you consider that case, okay? And let's say you, yeah, by the way, you represent mxy when you say it, that's in fact mx plus j times my. So you would be representing the mx and my values as a complex numbers. So if you have seen the videos, you would already see that this would make your life much easier while representing the values. So this is your real axis, imaginary axis of a complex number. And on the real part of this would be, of course, this mx, and imaginary part would give you my. So anytime you take the real and imaginary parts of this mxy, which is a complex number, would give you respectively the values of its projections on x and y planes. Okay, now suppose consider this is an m naught value, okay, which is there after you withdraw the b1 value. Now if you assume that there is no t2 decay, what would happen to this m naught value? Okay, let me write it as maybe mxy of t. In this case, what would be that value over time? Can anyone tell me? I'm not assuming that there is any decay. I'm assuming that there is no decay. So we would, as in the next step, we will come to the decay part. So what would be the mxy value with this? Can you tell me the expression, or first tell me what would happen then?
It will go in a circular path.
Correct. Very good. So it keeps rotating here. Yeah, in the intuitive explanation I gave in the video, there was a mistake that I wrote here j omega t. That should be j times minus j times omega naught t, because it rotates in the clockwise direction. Okay, this rotation you could figure out from the right hand rule for the cross product. Okay, that's where you would figure out the direction as well. So mxy of t would be equal to m naught times e power minus j omega naught t. Okay, so next step is what would happen with T2 decay. Okay, there is a T2 decay now. This decay is there. Now assume that you have, again, this is your mx, and here j times my you are having here. This is your initial value. What would happen now to the initial value? Will it still rotate with a frequency of omega naught radians per second?
Yes.
Yes. What will happen to its magnitude now? Will it remain as m naught, or something is going to happen to that? Its amplitude. So you would see, because of the T2 decay, its amplitude would be decaying. Okay, and the decaying factor is given by this T2 constant. Okay, please refer to the derivation where we did it in a very detailed manner. So if you want me to write mxy of t would be now, its amplitude will be decaying as a function of t2, m naught into e power minus t2. Okay, and of course it is still rotating at j times omega naught t. Is that fine? So then, of course, we have worked out in the recorded video lecture in a similar lines what would be the value of mz of t. Okay, so in fact this value would eventually gain its value to m naught, then that is dependent on t1 constant. So you will get there e power 1 m into 1 minus e to the power of minus t by t1, plus if you have initially mz value of 0, that of course would decay with time. Okay, you could actually combine them and see it in a different perspective also, but this is good enough for now. Okay, this is what we have done in the first video lecture. And when it came to second video lecture, we generalized it, the whole expressions, to two cases. One being here our assumption is that your object is homogeneous. So you considered inhomogeneous object here. That's one further relaxation we made. And then we also considered here you have spatially varying and time varying magnetic field. Spatially and time varying magnetic field. What is the magnetic field here? B. Okay, that's what we have considered in the second video lecture. So what did we do there? Say for example, what would be the impact of this? Well, as you move on spatially, the T2 as the object varies. Okay, properties of the object varies. So let me call new vector r bar. Okay, the whole spatial thing, instead of writing every time x, y, z there, let me use r bar there. So now this is a function of r bar. That's what would happen. And what would be the impact of this? This is a more critical one. Spatially and varying with the time. So you could call it as dynamic or whatever it is. So what would be the impact of it? So that's what we studied there. Let me again put some steps here. Say for example, b equal to, there is anyway b naught plus, on top of it you have a function that varies with spatial location r bar. That means I'm writing equivalent to writing x, y, z all there. I'm just writing with one variable and t. This is essentially what we are going to have. And most important thing I was emphasizing in that video as well is that you have this magnetic field in the z direction only. So if you want to write b as, for example, bx, by, bz, okay, so this is, these two are always zero, but only this component is there. That is what you are mentioning here. Okay, but this distinction has to be clear that this b spatially at different locations, this value is different, but it is always directed in the z direction. So if this point is not clear to anyone, this is the right time to stop me here and we could have a more clarity there. Okay, so this is your yeah, anyone have any question here?
So this is the assumption, right? That
No,
right now we have the field only in P.
no. This is not the assumption. See, B is something which you have in your control to apply. Okay. Now you applied one field B1. If you remember this RF field in the XY plane, okay, just to tip it, and then you withdraw it. And then there is no other field you are applying. Later you will be applying a gradient field that also in the Z direction. You will, this is under your control. See, M bar is not under your control directly, but B is something you are applying and M bar is a result of it. So M bar will have values in X, Y, and Z directions, but B which you are applying will always be in the Z direction. But this value you vary based on at which spatial X, Y, and Z and time values at which locations you are there, you would be going to modify it.
So although it's always pointing in the Z direction, we are varying the magnitude of it.
Exactly. Or to be more precise, I would call it amplitude. Of course, magnitude is also
Yes,
correct because
amplitude.
anyway, B cannot have negative values. You are right. Except that this
Yeah.
delta B
Okay.
could be negative, the whole could be positive. Okay, suppose if I have some B naught field like this, okay, I might vary something. This could be my delta B that I am adding here. Okay, R bar of T. Assume that this is my B naught of X. So I might be varying only in the direction of X. If I am doing it, I could add something like this. So I would rather call it amplitude to be just correct. Is that
Okay,
clear?
sir. Yes,
Sir,
sir.
Yes.
sir, do you mean it is rotating only in the XY direction?
What is rotating? See, B is not rotating at all.
I mean, like
B
B,
is
like
the magnetic field you are applying. See, notice here in our whole equation, this M, if you look at it, can have components mx, my, mz. But B, we are controlling. And if you go through the lectures and previous classes also, we were always writing even cross product while we are computing. We just keep the Z component there. Okay. The rest Bx, By are always zero there.
yes, sir.
Is that clear?
Yes, sir.
Good. So this you have to keep it in mind. Otherwise, you are varying gradients and all, then you could confuse it to varying the B value in different directions. Okay, that should not be there. Right. Now, if I am going to write what would be the associated omega value now, this would be equal to gamma times B. Is it not my omega value? So this is equal to gamma times B naught plus gamma times delta B time of R bar comma T. Okay. This is what we have been calling it as omega naught. And now let's call this as delta of omega naught now. That's the additional frequency. So that you could see now you have a control to spatially vary this. Okay. Then we derived the expression of what would be the M of R bar comma T. Okay. That's the derivation that's done in the last recorded video. Suppose if you have M naught, okay, first take a look at this, all this. So additionally, you have this field. So there is one term coming additionally because of this delta omega naught. Otherwise, what would happen? This is again, if I'm not saying anything now in the current context, you assume this is nothing but mxy of R bar comma T, because I have my B1 coil there, which is receiving this signal. Okay. So this magnitude is varying by minus T by T2. So that's your magnitude. And because of this term, it would be rotating minus G times gamma times B naught or minus J times omega naught. These are exactly the same expression here, like this expression only. But after that, you have this, and notice here, you have, for example, in the main equation, dm bar by dt, and you are computing m. Okay, for that you do integration on both sides. So that would give you here an integration of this exponential of gamma times, okay, or it's again, it would contribute to omega, would contribute to the rotating field, just like here. Okay, I could have written here if you want omega naught plus here, but let me write, because the term is a bigger term, I'm just writing it separately, minus j. Okay, here also it is rotating with minus j gamma times integral 0 to t delta b of r bar comma tau d tau. Okay, this is the crux of the whole rest of the class. So this term has to be clear to you. The additional term that has come because of this field. See, dB bar by dt, from that you would be dm bar by dt, to get m you would be taking integration. Okay, in the whole cross product, then what would happen is you could follow the derivations that we did in the last two classes. You would realize that then it is like integration from 0 to t. If you do that, that would give you m there. While doing that, what would happen? That would be equivalent to taking integration of this term, okay, from 0 to t. That's what would come. And anyway, this frequency would make it to rotate at that value. It's only is going to change the frequency. So that's why there is minus j here, just like you have. So here, if you want, I could write it as e power minus j omega kind of term would come. Okay, and now this delta, that would eventually delta omega naught. So integral 0 to t of delta of omega naught of this is dependent on time d tau. The time I'm just keeping it tau because there is upper limit of this integral is also t. To avoid that, I'm keeping tau here because I have used t here. Is this term clear? This is the whole crux of, or this is the one from where we proceed further to understand what is the signal that you are going to get.
Sir,
Yes.
I guess I'm getting a bit confused. The B value that we have originally written, B naught plus delta B R comma tau.
Right.
So here delta B is the corresponding to the RF signal we apply.
No, this is correspond to delta B is correspond to the gradient signal that you will be applying.
Okay, so the gradient one. Yeah.
Okay. So this you would be applying in the Z direction only. That's a very good question. If somebody is confusing with B1, this has nothing to do with B1.
This is, yeah, it's not B1, right?
Nothing at all.
Okay.
B1,
Okay.
we are done with the B1. Once you tip it to the XY plane, we forget about B1.
Okay. So, sir, the
why,
example which you...
That is why you have it in Z direction only now.
Okay.
Yeah, you are asking something else also.
Yeah. So in the video, like originally, while you were doing the derivation, you assumed like it's already been tipped off
Right,
to
correct.
the transfer plane. So
Exactly.
that tipping off was done due to B1.
Exactly, correct.
Okay.
B1, we use it only to tip it off. That's all.
Okay, sir. Okay.
Very good. So any other questions? Okay, good. Then I hope you all understood that. Now we would consider this is the key expression. Okay, so that's why let me write one more time here. M of r bar comma t is equal to m naught is your magnitude. This magnitude is way decaying with the time because it is transverse with T2. This usually would rotate with just the presence of omega b naught with e power minus j gamma naught. Now you got the additional field also. So there is an additional rotation or a resonant different resonant frequency, which varies over time. So that delta of that value, by integrating because you are computing it to t. So you do it from 0 to t, right? This delta b, which is a function of r bar and time, this you integrate over tau. That's your, we arrived at the final expression by relaxing all the or by removing all the assumptions now. Okay, so after that we are in fact considering some special cases because those are the ones which you would come across in practice while doing many things. So one thing is you still consider it's a static field. Okay, that means this is not dependent on your b of r. Yeah, so your b delta b, so whatever you are writing here. Okay, so although delta b of r bar comma t is in fact you are assuming it to be varying spatially only but nothing to do with time. So that's the first case you are considering. And further you are also considering here spatially varying with respect to x only. That's the first case we considered in the video. So spatially varying with respect to x only. Okay, with a gradient of db. I could write dbz also. There is no problem with that. Okay, I could write as b itself because anyway it has only bz. Okay, dbz by r of t by dt. I consider it is varying with, sorry, this should be, this is varying only with respect to x. So I could write dx equal to gx. In other words, I could write here my function delta b of r bar comma t is equal to gx times x. Okay, this is the function I'm considering for this particular case, where you could think of for a given yz plane, this is constant. Okay, for a given x value, with x it is varying linearly, in other words. Okay, suppose this is my x here. Okay, so this field is varying linearly and that slope is given by this gradient field which you would have under your control. Okay, so then it's very simple. You substitute this in the above expression one, if I call it, in that you substitute. So what would you get then? This has nothing to do with the time. So but you are integrating with respect to time, so you just get t there. 0 to t d tau would get this. This is nothing but your tau is varying from 0 to t d tau, so you would get simply t there. So what is your expression there? M of r bar comma t equal to m naught into e power minus t by t2 e power minus j omega naught into e power minus j times gamma times, what do I get there? Gx, g subscript x times t. Or you could write the omega value. In fact, it would rotate with a value of uh, omega naught plus gamma times gx times x. Okay, with that value, this is going to rotate. That's the first case we considered. Is that clear? So the case 2 we considered is still static magnetic field. So static b naught value or static b value. Okay, that means your still b of r bar comma t is only b of r bar. But now you are going to vary, how you are going to vary is, now this has r bar comma t by dx equal to gx, okay? Gradient in x direction is there. Similarly, you have gradient of it in the y direction, okay, which is gy, and also gradient of it in the z direction, which you call it zz. In other words, your delta b of r bar comma t will be equal to gx times x plus gy times y plus gz times z. Again, for notational convenience, I would write g bar as a vector with gx, gy, zz. Then my delta b of r bar comma t is equal to g bar dot what? R bar, right? So again, you notice here, this has nothing to do with, this is your delta b of r bar comma t. You again substitute here, okay? So again, it has nothing to do with the, this expression has nothing to do with the time. So just gets multiplied with the time. So what do you get there as an expression? M of r bar comma t is equal to m naught into e power minus t by t2 into e power minus j omega naught into e power minus j times gamma times, what should I write here? G bar dot r bar times what? What do I get here? G bar, sorry, there is a t here. What do I get here? Times, hope at least someone is with me. I'm not left alone. Times what? What do I get here? Minus j, you look at this expression, okay? So delta of b of r bar comma d bar, I could write it as g bar dot r bar. Now I need to integrate with respect to tau varying from 0 to t. So what do will I get here? What is it still missing here?
T.
That's it, t. Good. That's your expression. And the last final case that we have discussed in the last video lecture, I'll go there. In addition, you have here varying magnetic field, time varying magnetic field. That's all you have. Time varying magnetic field. Okay. So which I could write it as now, how could I write then? You come here. Okay. So this is a time varying magnetic field. So I have to write it yeah, then this of course is the expression, you time varying magnetic field is there, and also you consider, so how do I consider that? So delta b of r bar comma t equal to, now I have g bar is varying with the time, in fact, okay? That expression gx of t, gy of t, gz of t, those gradient values are varying with respect to time. G bar of t dot r bar is what I would have, okay? So then what would happen is, you get the same expression here, but the last one you have to integrate. So I will just copy paste it rather than writing from the scratch. Okay, I hope I could do that. Control C, Control V. Okay, good. So then only this part, the last part would be varying there. So what would happen here? Minus j times gamma into, okay, integral over 0 to tau g bar of t. No, I should write g bar of tau there, is it not? Because the integral variant I'm using is tau here, dot r bar, okay, g bar of tau dot r bar into d tau. That's it.
So you can change the limit to t actually.
Yeah, sorry, you're right. That's t only. Good. That's the expression. So that's the Again, this is from here, we start for analyzing our signal. So far clear? This, unless you have gone through the videos, you might find it I think too much of math is there, and you feel like we have gone through it fast. But once you go through it, this should be more or less, if you have not gone through it yet, but if the intuition is clear, we could go ahead with this. You have any quick questions? You have any questions here? Not necessarily quick.
So how do we get G values?
Yeah, very good. That is what we apply. That is what actually we are going to vary in order to decide where we want to have the signal from. That's a very crucial part. Gradients, it is we who modify those values.
Okay, so we apply this delta B of R comma T with the gradient quotes.
Correct, correct. That's what you
Okay.
not only apply but vary with time in
Okay.
order to have a control over what exactly you want to get out of this.
Okay, sir.
Yeah.
So what part exactly will this thing affect?
Yeah, maybe that's what signal equation, once I write it, this should be clear to you.
Okay, sir.
That's what we will do now. If there are no questions, we will move on to the signal equation. Now we will see what is finally we are going to get the signal. Unless I have this equation, it's very hard to explain what is it we are getting out of the RF coil. What is it that you are receiving from the RF coil? Okay, is everybody with me so far? If so, I'll move on to writing what is the signal we have been waiting for so many days and weeks to see what's the signal you are going to get out of it. Okay, so let me write that now. Whatever signal you are going to get, let's call it as SR of T. What would be that is, see, this is going to, by the way, just let me make one more change. Wherever there is T2, in fact, you replace with T2 of R bar there, okay? Because that's you are considering that your sample is non-uniform, inhomogeneous sample. So that's what you do it. Other than that, it's not going to change anything. Okay. So now what would be the signal that we would be getting will be entire the volume of your one. If you take all put together, that's what would give you the signal M of R bar comma T. Okay, integrated over accumulated. See, you have put a sample inside, you applied these magnetic fields. Okay, at a given location, R is XYZ, at a given XYZ location, this is what you would be getting. You take the whole sum of all things that are there within that sample, that should give you the signal SR of T. So in other words, I could write it as integral, or this would be equal to integral over X, Y, integral over Z for your whole sample. Okay, the initial value, let me call it as M subscript S of XYZ. That's my initial value which I obtained through B1. Okay, that into e power minus T by the whole thing. M of R bar comma T will come inside here. Okay, this whole expression would come here. T2 of R bar, right, into e power minus J times omega naught T, e power minus J times gamma into integral over 0 to T. Okay, G of tau. Okay, dot yeah, anyway, G bar, am I writing it? Okay, G bar of tau. Okay, if I'm writing it as G bar, or yeah, I think R bar, so G bar is fine to write. G bar of T dot R bar times D tau, right? This whole into dx dy dz. That's the signal we are going to get. Now again, we could actually, by varying the, so first case, you consider the first case where we considered it is very, so your frequency is varying for given every given value of X, it is different, right? In the similar way, we will discuss that part again later, but for time being, you assume that you could excite and get signal from only one slice. Okay, how you do it? Similar to this, you give one frequency only, you excite B1, that excites only a given slice, and from that you will get it. I'll come back to that in the coming lecture. Okay, but for the time being, you make some assumptions here. Okay, first assumption you make it is constant 2D. Okay, there is only, consider only 2D image here. Okay, consider 2D image only. So forget about Z. How you could excite only particular value of Z, will come to that later. Okay, that's one assumption. So second one, also ignore the value of T2. So when to take the field and what's going to happen, for the time being you forget about the way it is making changes to the amplitude. Okay, that this is not very crucial as such, because you will understand it a little later, but for the time being you make those assumptions. So then look at what is the expression that you are having here. SR of t equal to, now integral over x, integral over y. Okay, then since I am taking only 2D image, okay, I will call something, how do I get here? Only a particular, this would have, yeah, will have the resulting those voxels which are there. For example, this is something which is exciting Z naught minus delta Z by 2 to Z naught plus delta Z by 2. Okay, these are the locations where you get the response. This I would make it clear to you in the upcoming class. So for the time being, you assume that what you receive is only, you made it in such a way by applying a gradient in the Z direction, that for a given slice plus or minus delta Z by 2 is all you are going to get the value from. So m naught of x, y, z into dz, that's your m of xy. So I'm going to write here, then this is only a function of x and y now. Okay, because I'm going to excite, dz is taken care here. Okay, into e power minus j times omega naught t into, okay, and exponential of minus j times gamma into, I'm just repeating the same expression here, 0 to t g bar of tau dot r bar times d tau into dx dy. Is everybody able to follow with me here? Any questions here? What I have done, I just ignoring this amplitude here. Okay, that you could compensate later, we will see that later. Okay, it's not a very crucial thing here. All that is doing is whatever magnitude you are getting here, that's getting modified, that we will see later. Second thing, you assume that you are somehow magically are able to bring into excitation only at a value z naught, and of course with from delta z in the z before and after. So that is giving you, instead of m naught of xyz, you are getting m of xy, and the rest I am writing the same expression. Is that clear to everybody? Any questions? Sai Pavan, is that clear?
Yes, sir.
Okay, so then this is where you could actually, how do you get rid of this signal? I want to get rid of e power minus j omega naught t. All you need to do is, you simply, this is your classical communication. So you demodulate SR of t, okay, with e power j omega naught t, or in other words, you write S of t equal to SR of t into e power j omega naught t. Okay, that new signal after demodulation. Okay, you all know demodulation, right? You just need to get rid of this. You multiply with that. So then let me write my signal as m of x comma y exponential of minus j times gamma 0 to t g bar of t dot r bar, sorry, this is tau r bar into d tau dx dy. Clear so far? Now what I am going to do is, See, G bar, as I was mentioning, is under your control. Suppose if I'm applying this as Gx into x, comma, Gy into y, comma, 0. This is the gradient that, sorry, I should be writing it slightly to Gx into x is what I would get. So I'm going to apply a gradient of Gx, okay, that could vary with the time, okay, Gx of tau, Gy of tau, 0. So this function still I am not deciding what is the function. It could be a simple linear as I have written there, but that's a function over time. Okay, Gx of tau and Gy of tau. This you won't be applying ZZ component anymore, because that you would be using to figure out at what Z value you want to get that. So you are going, in other words, you are going to vary your gradients based on the locations that you are there in X and Y as a function of time. Is that clear? So then you substitute, then you also write here two new variables kx, for example, which I would define it as gamma by 2 pi into integral 0 to t gx of tau. Hopefully you are sensing where I am going now. Gamma by 2 pi into integral 0 to t gx of tau d tau. I am writing it as kx. My ky is gamma by 2 pi integral 0 to t g of gy of tau d tau. These are my new variables I am defining here. Now you substitute this here, okay, g bar of tau is there. So what is it that you are getting there? Your s of t equal to integral over m of xy into exponential of minus j times gamma. Okay, if you want I will write one more intermediate step also, g tau into what is this dot product, that's equal to gx of tau times r bar is xyz times x plus gy of tau times y into d tau. Okay, this with respect to dx dy. Okay, now I could separate these two integrals here and use gamma by 2 pi into this with kx, replace that with this variable. Similarly, gamma by 2 pi into gy of tau d tau, you replace that. So what is my s of t now? Can anyone tell me this expression? Double integral m of xy into exponential of e power minus j 2 pi into, what am I getting here?
kxx
Yes,
plus kyy.
very good. Did you
Fourier
finally see the
transform.
expression you wanted?
Yeah, Fourier transform of m of x.
Very good. This is the two-dimensional Fourier transform. And maybe this is a two-dimensional Fourier transform. For just I will write, maybe I'm not sure how to write F2 or 2D or two-dimensional Fourier transform. Let me keep a hyphen so that it will not be a 2D CTFT. I'll write to avoid any confusion. Two-dimensional CTFT of m of x comma y. Right. See now, you have control over kx and ky. Is it not? How do you control kx and ky? You have a control over gradients of gx of tau and gy of tau. You have a control over that. And with that, of course, this is also dependent on time here. So as you are taking at different times, or by modifying this term at a given time also, you have a control over kx and ky, and you are capturing the m of xy in the kx ky plane. So you have kx ky, you vary kx ky, you get a sample, and of course you need to demodulate that sample with e power minus j omega naught t, and then what you are getting are the in the sample space of 2D ff 2D CTFT, you are going to get these values. And then how do you get m of xy? Is simply you take inverse CTFT of it. Okay, CTFT inverse of it, of this function. If you take it, right, that would, anyways, you won't reconstruct it that way. Hope you all remember Fourier slice theorem to get, see, this is at a given point you are getting it, but you want it to construct in the spatial domain, both x and y. Okay, so Fourier slice theorem, if you have at a regular grid with enough number of samples, you should be able to reconstruct the signal back in the spatial domain. CT, there was an issue with Fourier slice theorem because by default there, with the Radan transform, you are getting the results, acquisitions radially in the Fourier domain, even if you are moving to the Fourier domain. But here it is under your control, the kx and ky, you control them in such a way that you could get the acquisitions of this signal, you acquire this signal, okay, at regularly varying kx and ky values. And then you simply use Fourier slice theorem to get the signal back in the spatial domain. As far as I know, this is the only modality, okay, that's known where the image is acquired, where the signal is acquired, to be more, even more general, in the Fourier domain. And from that you get the spatial domain signal by taking the inverse two-dimensional Fourier transform. Is that clear? Hope you are getting some excitement with seeing this result. This is a very, yeah, very classic, very elegant result. Hope this is clear to you guys. So I will, if maybe I could, if you have any questions, I think this is where I would stop. We had, I think, yeah, somewhat a good stretch for your brain muscles. So I think I could stop here. Okay. Anybody have any questions here before we move further? I think, yeah, this is all for this class. So if any questions, maybe I'll meanwhile pause it so that the video would be, yeah.
Sir?
Yeah, just 1 minute.
So,
1 minute. Sorry. Yes, tell me.
so what do we do by controlling kx and ky actually?
By controlling kx and ky, you are figuring out at what values of kx and ky you would like to acquire the signal. See, this is nothing but whatever signal you are getting is a two-dimensional CTFT, right? By controlling kx and ky, you are dictating, or you are figuring out where you would like to, wherever you want to acquire the signal in kx ky space. By controlling this kx ky values through these gradients, you could acquire signal for that particular values of kx and ky. And once you take enough samples of it, okay, all the Fourier analysis that is required has been already covered. That you don't require anything almost more than that. You won't, you would hardly require, okay, be it sampling and everything. You have all those concepts with you now, and using that, then what you would do is you take enough values of kx and ky. Again, this, you know that it is related to the aliasing part. Once you do that, you have it, then you will be able to get the 2D signal. See, you have an object in the spatial domain. If you have enough samples in the frequency domain without aliasing, you would get back the signal. So accordingly, you would figure out with what spacing of increments of kx and what increments of ky you need to acquire the signal. You would accordingly modify them over time by suitably selecting this gx and gy values, and then getting that signal here. Once you change the gradients, you put it at the one you want, and then you acquire the signal. So that would fill samples in the kx ky space, and inverse transform of it would give you directly the 2D image. Is that clear?
Yes, sir. Like to some extent, like we are generating the Fourier transform and then taking the inverse Fourier transform to get m of xy.
That's right. That's right. And you are controlling this kx and ky yourself, okay, so that you would figure out at what kx and ky the signal corresponds to.
So, but what does this image m of xy represent? It's is it the image that we want to get?
That's right. So in other words, see, you are making, see, this M of xy would vary depending on the tissue that you have there. See, even when you have a light, can you ever see the image as such? It's only there you are seeing the reflection, how based on the properties of its absorption and other things, you are making an inference of what is there at that point. So you would always see some property of it getting modified, and that's how you would infer what's the object is there. And here the property that you are inferring here is M of xy, which is the magnetization field it is generating, which is dependent on your applied magnetic field B naught, along with that the proton density that you have. So that now you could make a distinction between which kind of soft tissue it is, because within the different types of soft tissues could have different proton densities, or bone, it's a completely different. So that's how each one with a different proton density would eventually give you different M of x comma y values. So here the property, so you are inferring this essentially would different kinds of tissue properties, okay, the different kinds of materials, okay, or inhomogeneity if you are considering, that would give you a different response there. From that you would know what is there.
Okay, sir.
So it is essentially you are saying what is there at that point. In other words, you know that if it is a gray matter, this is what I would expect. If it is a white matter, this is the kind of M of xy I would expect for these values of excitation times and other things. If it is a bone, this is what I would expect. You know that. From that you would infer what is there at that point. It is not the light. This is the magnetic field you are looking at.
Okay, sir. Yeah.
Good. So any other questions?
So this is better than CT scan, no, sir, as you don't have to interpolate anymore.
No, see, interpolation is just one aspect of it. You are right. If I am going to use, for example, only Fourier slice theorem, then MR, it is the best case. MR, there is no problem at all with Fourier slice theorem. But in CT, that is not the main bottleneck, because you, instead of using slice theorem, we have seen the convolution back, what is that? Back projection, right? CBF method we have seen, or filtered back projection. You use this, then there is no question of interpolation. But the issues there are bit more different. That there, the phenomena you are using is absorption of radiation, gamma rays. That's what you are looking at there, which is having a radiation effect. But certain structures, where you cannot see much of a distinction with M of xy, but perhaps that would, certain structures would respond well there. For example, with bones, you get a very good contrast there. So it has its own pros and cons. But the beauty of this is there is no radiation effect, okay, and you are in this is working in the radio frequency, and you are making use of the abundant hydrogen atoms that we have in our body, be it in fat or in water or in any tissue. That's the key difference.
Okay, sir.
So also, since we're generating a digital image ultimately, so we can vary kx and ky only for integral places of x and y, right?
Right. See, even your image is basically a discrete one, correct? So image is also not a continuous one. So eventually you would be getting a discrete one only. Even after all, an image is 256 by 256. When we say it, it's a discrete one only.
Yeah. Okay, sir.
Any other questions here? Okay, then I'll stop here. Maybe I will take just 1 or 2 more classes on MR, and I would like to give you at least take you through some of the segmentation methods. Let's see what best I can do there. Maybe I will not extend it too much. See, after this, this MR imaging itself could be a complete course in itself. Okay, last time I covered something else where what are the kinds of RF pulses you would use, and what is that you would be getting, and different types of acquisition protocols is what I covered last time. But this time I felt like giving more better appreciation on how you get the signal out of it is better. So that's what I spent it there. But nevertheless, with this background, now if you want to work in MR imaging or want to become an expert in MR imaging, now you have the kind of platform, the base is ready for you. So you work on it, you pick any good book there. For example, most of the concepts I have taken from Nishimura textbook. That's really good textbook. Okay, it has a bit high standard, so you will see direct steps there, intermediate steps you need to work out, but the standard of it is pretty good. So you pick a book like Nishimura, or even for that matter, the J. Prince book also is very good. Signal medical imaging, signals and systems book. That's also is very nice. So you pick one of them and continue your reading. And I hope this made clear to you the basics that are required. And you now have all the background required also. For example, your DSP background, particularly the 2D sampling and all these things and Fourier transforms are very clear to you now. We covered, we have taken enough time in revising and working out, extending them. So I think you could do very well with this given background if you want to further pursue MR. I will not take you through acquisition protocols, but I may take maybe just 2 more classes. With that, I will wrap up MR imaging, and I will give you tell you something about segmentation after that. Okay, just let me, with that, I will stop the recording part.